Hello everyone, this is Xiaobing. I'm a software engineer from StarTree. Today I'd like to share how we efficiently handle Upsert at scale in StarTree Cloud. So Upsert might sound simple at first, but doing it efficiently, particularly in a real-time analytics system like Pinot, can pose some unique challenges. So let's dive into those challenges and see how we have tackled them. Then we'll explore how Apache Pinot implements Upsert. And we'll look into how we have scaled Pinot Upsert in StarTree Cloud then. And finally, we'll touch upon some enhancements we are considering. So what is Upsert? Essentially, it's an operation that combines insert and update. If the record isn't in the table, we insert it. If the record already exists, we just update the existing one. So the table needs to have a primary key so we can check if a record exists or not. But why do we need Upsert anyway? It's usually an atomic operation, so which can check and update the data atomically. So we don't need to worry about the concurrent updates when we use Upsert to correct the data. So it simplifies a lot when we want to keep data in sync between the source and the tables. We see Upsert in online transaction processing systems. And Upsert is relatively easy to implement there because those systems typically use role-based storage, which makes it easier to update the record and even allows in-place updates. And they also have indexes for efficient point lookup based on the primary case. Then for the Upsert in those systems, it can be a simple point lookup with the index. And if the record is found, we update it. Otherwise, we insert it. And also very important here is once data is inserted or updated in those systems, it can become queryable immediately. So what about the OLAP system? And things can get complicated in those online analytics processing systems when doing Upsert. So first of all, there are need to modify data in OLAP systems as well. For example, we may want to update trip fares or change the order status later on, and we want to make those changes in the OLAP systems as well. But OLAP systems usually keep data immutable once they are ingested in order to apply some optimizations like columnar formats, compressions, and even tracking some statistics about the data chunks. So the analytics query can be executed efficiently on larger data sets. But those optimizations can make Upsert a very expensive thing to do because when we're changing the data, we also need to redo those optimizations. So there are some common methods here, like copy on write, merge on read, and some background compaction techniques to make Upsert able to work in OLAP systems. But those methods are not really designed for real-time Upsert. Now, what is real-time Upsert anyway? So real-time Upsert will mean low latency on both ingestion and query size, and also the latencies should be kept low even at very high data ingestion rate or query rates. And particularly, this also means the Upsert data should become queryable immediately once ingested, and this can be very challenging for OLAP systems to achieve. With those as background, we can start to talk about Apache Pinot and its Upsert. So Pinot is a real-time analytics database supporting data ingestion within seconds and query response in like milliseconds. Pinot can achieve this at a massive scale, maintains the performance in order for real-time analytics workload. As shown in this figure, Pinot support streaming data sources, batch data sources, and able to support use cases like dashboarding, anomaly detection, and all within real time. So how does Pinot do Upsert? Basically, it also has to check the existence for each incoming record based on their primary case to decide whether to insert or update. And as required for real-time analytics, the data becomes immediately queryable once upserted, ensuring no latency between the ingestion and the queries. And so at a high level, Pinot Upsert works with real-time table, and real-time table ingests streaming data sources. To handle Upsert efficiently, the data stream must be partitioned based on the primary case. So like in this figure, the primary key 1, 2 has to go through the partition 1, and the primary key A and B go into partition 2. And those partitions are handled by individual servers. So those servers can handle the Upsert workload independently. And we can scale the Upsert workload by adding more partitions and more servers. So let's look inside a single table partition. So the segments are kept immutable once they are committed. But even though Pinot can maintain a mutable Upsert view on top of those segments, and this Upsert view continuously get updated to reflect the real-time data changes. And the queries just access this view for the answers. As we can see in this figure, every individual segment has this Upsert view. And how can we achieve this? So to implement this, Pinot introduced two critical data structures. So first we have this Upsert metadata, which is used to track which record are stored in the segments. Like in this figure, the primary K1 is in segment 1's first document, and the primary K2 is in segment 2's second document. And second, we have this valid doc bitmaps, which marks which document are currently valid in every single segment, and only the valid document will be processed by the queries. So how those two data structures going to be used by the data ingestion pass and the query pass? Let's go into those details in the next few slides. So during data ingestions, Pinot checks if the primary key already exists in the Upsert metadata. So if it's not there, it just insert the new record, mark it valid, and also update the metadata to pointing to the record location, which is in the consuming segment. If it does exist, Pinot will compare the incoming record with the existing one based on some comparison columns, which usually is the table's time column, which means the most recent record will win the comparison. And if the incoming record actually lost the comparison, it still gets ingested, but it's just marked as invalid, so it's not visible to the queries. So while on the query pass, each segment, in normal Pinot tables, each segment will return a bitmap after evaluating query filters. And this bitmap will provide the matching documents for the following query operators. But for Upsert tables, we actually end this without bitmap with the valid doc ID bitmaps, so that the following query operators will only process the valid matching documents. And as we just mentioned, Upsert is just a data view. So users can actually bypass this view by setting this query option called skip Upsert. And this allows queries to process the raw segments directly, and this can be useful for some debugging use cases. So what we talk about is about the full Upsert in Pinot, which means every single incoming record is a complete record with all the columns. And on top of this, we also added a partial Upsert, where incoming record doesn't have to specify all the columns. Instead, the partial Upsert is merged with the previous record to derive a complete one. And this complete record will be processed by reusing the full Upsert logic. And there are different policies here to decide how to get this complete record by merging those partial Upsert with the previous one. For example, there are policies to just take the max of the record between the new record and the previous one. Also, there are policies to combining all the values together, so we get all the values for columns. We also have this. We also added this deletion support here, so users can insert a tombstone record to delete some primary key in the tables. So that's how Upsert looks like in open source Pinot, but there are actually some challenges to scale Upsert for Pinot here, and the major one is the Upsert metadata store, which is implemented by using concurrent hash map in open source Pinot. So as the metadata size grows, it can consume significant heap space, which can cause frequent Pinot pauses. And also it will compete the heap space with the ingestion workload and the query workload, impacting their performance. So besides rebuilding this large Upsert metadata can also takes a lot of time when the server gets restarted, because everything is kept on heap, it will be lost when the server started. To address those challenges, we have added some improvements in the open source Pinot. For example, we have introduced the metadata TTL, so we can clean those metadata regularly and to reduce the heap usage. And also we added this disk-based snapshot for those valid.id bitmaps. So when server get restarted, we can just look at those snapshots to rebuild the metadata faster. But this is not still enough for the customer we see in StarTree Cloud. So we have taken those improvements even further here. And to address the heap usage, we have used RocksDB for the metadata storage. And it moves the Upsert metadata off heap. And RocksDB also provides a lot of configuration knobs to control the memory usage. So we can customize the Upsert configurations for different workload need. And with this, we could support like even billions of primary key on single servers as we see in some customers' environments. And this dramatically improved the scalability for storing Upsert metadata. Besides, the valid.id bitmaps are actually still kept on heap, which means the query performance is not really impacted by the choice of the metadata store. And by actually offloading the metadata off heap, the query performance can sometimes be improved because the pressure is getting reduced for those query workload. Additionally, we also use a new minion task to preview the snapshot of Upsert metadata, which essentially is a set of RocksDB data files here. And RocksDB allow users to import data files directly. So based on this RocksDB feature, when server get restarted, we can simply import Upsert metadata to reduce the metadata rebuild time. And those pre-built Upsert metadata is kept in deep store, so it's a lot more reliable than keeping the snapshots on server's local disk. And by this way, by the way, minion here is Pinot's built-in auto-scaling task framework, and to handle complex data processing outside of the Pinot servers. So when we pre-build those Upsert metadata snapshots, the Pinot servers can continue to process the ingestion and queries. So as we have seen in some production environments, this new task can be very effective to bootstrap metadata. So like in this case, without this new task, the server is pretty struggled to get started up. Well, after enabling this task, the server could start in just a few minutes. There are also some other challenges here for Upsert. For example, the invalid documents are not really deleted from the segments, and it can waste a lot of disk space. So in the open source Pinot, we have introduced a few new minion tasks. For example, the Upsert compaction task and also Upsert compact merge task, which can remove those invalid documents. And if the segment size get very small, these segments can also be merged up into bigger ones to improve the query performance. So in StarTree Cloud, we have this segment refresh task, which already used by a lot of customers to optimize their data segments. So we just extended this segment refresh task to support Upsert table as well. So this task can remove those invalid documents and merge segments up to bigger ones to improve the performance for Upsert table as well. And the user doesn't need to specify a different task for this purpose for Upsert tables. So that's how we have scaled Upsert in StarTree Cloud. And looking forward, we are planning to consolidate the compaction merging and the snapshot creation minion task into a single one, so it can simplify the operation a lot and also improve the correctness or reduce the chance of risk conditions if when running multiple tasks for a single table. And also we consider to enable StarTree index for Upsert table. And StarTree index is a very powerful index. It can, for a certain workload, it can improve the query performance dramatically. But it doesn't work for Upsert table today because StarTree index is made for immutable segments majorly. But for Upsert tables, the segments are made effectively mutable. And how to make the StarTree index for changing data is something we are looking into. So the StarTree index can also benefit the query performance for the Upsert tables. So that's all for today's talk, and thanks a lot for your time.